No, I need to see that.
Bringing the test, the camera on test days and just like putting it towards the students just to like videotape the process of them taking a test. It would be a violation of any number of university policies, but it would also be fun. So anyway.
University policies.
Policies?
Like what?
What? I follow policies.
Oh, really?
What? I don't like where this conversation is going. Let's begin with a word of prayer. So, Dear Father, we thank you for this day and your many blessings. Just pray that you'd be glorified in what we do, and that we all understand a little bit about the residue calculus today, Lord. In my prayer, Lord Jesus. Amen. So, yes, we will hopefully by the end of business today be talking about residue theory. We do have a little bit more theoretical stuff to build up before we quite get there, but we'll get there. So I'll just entitle this lecture Residue Theory. And so I'm going to start with an analog of the factor theorem. It's like pretty close in spirit to what I did last class. This is theorem 9.2.6 in my notes. Let Z naught be an isolated singularity of F. Then Z naught is a pole of order n. If and only if f of z can be written as g of z divided by z minus z naught to the power n, where g of z is analytic at z naught with g of z naught not equal to 0. All right. The proof is very simple. Here's how it goes. And we'll do the forward direction, as the reverse direction is pretty much just the same thing. So here it goes. If Z naught is a pole of order n, we have what? F of z is equal to, let's see here, a sub minus n over z minus z naught to the n power plus dot 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 plus, oh, this is not the way to do it. I'm choosing the most horrible notation. Let me retract my statement. Let's just write it in summation notation. So we have a sum, let's say n equals minus big N to infinity of a sub n times z minus z naught to the power little n. All right? But I can rewrite this as the sum something to infinity of a sub n times something divided by z minus z naught to the power n, big N. If you want, I'm gonna change this little n to an m, as in mommy, just so you can see a little bit of a difference. Big N as in nenu nenu. So there we go. So if I do that, what do I have to do to be fair? I'm factoring out a 1 over z minus z naught to the big N, right? So this becomes not m anymore, but what? M plus n? Is that right? Oh yeah, duh. I wanted to subtract. I don't know what's wrong with me. So, and of course that still starts from where? M equals minus n to infinity, right? But, we can rewrite that as I mean, we don't really need to do anything more. This up top is the g of z, right, that we're after. And is it holomorphic? Maybe one more step just to make it manifest, yeah? So this is equal to the sum, let's say j equals 0 to infinity of a sub what times z minus z naught to the power j. So I'm letting j equal m plus n to make this transition. So if little m is equal to minus n, that means j is equal to 0. So my starting bound is right? And my a sub m is really a sub what? N, oh, j minus n? Right. So with that, I mean, I think it was already clear before I did this, but now it should be just like manifestly clear that this is analytic at z naught, right? Because it is a power series at z naught. And how do I know the power series converges? Because I'm starting with the Laurent series for the pole of order n, which we're given converges on a neighborhood of this isolated singularity by the definition of isolated singularity, right? So this is a analytic function at z naught, and what's its value? If this thing on the top is, what is this? If this altogether, the numerator here, right? If this is my g of z, what's g of z naught? It's the constant term, right? Which would be a sub 0 minus n, also known as minus n, which is given to be not equal to 0. Why? What did we say? What? Because we said so. No, because z naught is a pole of order n. I guess I didn't say so, but I'm assuming that we have z naught as a pole of order n, which is to say that the leading negative term here is, you know, like it's assumed that a sub minus n is not equal to 0. That's what makes it a pole of order n. So there you go. We've proved that it has the form g of z over z minus z naught to the n. And to go the other way is very simple, right? Did you guys see how the argument goes the other way? You just, you know, you have g of z is equal to, let's say, a sum of b naught, listen to me, b sub n z minus z naught to the power n, you know? And since g is analytic, with g of z naught equal to 0 here, right? And if you look at f of z equal to g of z over z minus z naught to the n, that's what we're assuming, right? F of z has this form, then that's exactly, I'll just write out in this kind of notation, b naught plus b1 times z minus z naught, you know, divided by z minus z naught over n, which of course is equal to b naught over z minus z naught over n plus, you know, b1 over z minus z naught to the n minus 1, and so forth and so on, right? Which shows you that it's a Laurent series with the leading negative power of this one right here, and the coefficient is non-zero, therefore it's a pole of order n. Yeah. Okay, so this is the, you know, the analog of the factor theorem we talked about last time, right? If we have a 0 of order n for a holomorphic function, an analytic function, then we can factor out, you know, z minus z naught to the power, to the order of the 0. So an example based on this one, example 1 here. If we look at f of z equal to e to the z over z minus 1 to the power 5, What can you tell me about z naught equals to 1 for my example here? Yeah, it is a pole of order 5, right? That is a direct application of theorem 9.26. Why? Note, e to the z is analytic at z naught equals to 1. And what is e to the 1 equal to? Well, it's not equal to 0, right? So we have the terms and conditions met to conclude that it is in fact a pole of order 5. Yay. The next example requires a little bit more calculation, but let's go through it because we could all use some practice. And here we have f of z equal to sine of z plus 2 to the power 5. I think that's all inside the sine, I believe. Divided by z plus 2 squared. Right? So the question here is, sorry, just a second. There's a typo in the notes right here, I think. Let us fix it. All right, so I wanted to put a third here and a 5 down here. All right, and to be clear, I'm putting all of that into the sine function, okay? Are we good? Now I cannot apply the theorem directly, right? Because if I tried to make g of z sine of z plus 2, and I'm thinking about z naught equals to minus 2 to be clear, okay? So this has a divergence at minus 2, right? We get division by 0. That's a singularity. It's in fact an isolated singularity. So I can't make g of z the numerator function because it's 0 at minus 2 because sine of 0 is 0, right? So we have to do some calculation before we can apply the theorem. Here's how we do that. So this is 1 over z plus 2 to the 5th power times the power series for sine. Now remember, sine of theta is what? It is theta minus 1/6 theta cubed plus 1 over 120 theta to the 5th, and so forth, yeah? It's the Maclaurin expansion for sine. So we can make a substitution here, and what we get is z plus 2 to the 3rd power minus 1/6 z plus 2 to the 9th power plus 1 over 120 z plus 2 to the, 15th power, and so forth, all right? So now we can do algebra here, all right? And this algebra is supported by the theory of uniform convergence for power series. This allows us to do term-by-term algebra, basically, without getting into trouble. So anyway, this gives us 1 over, let's see here, we can simplify this, right? We really have 1 over what? Z plus 2 squared? Yeah, if we do that, then we'll have 1. So I'm just factoring out of z plus 2 cubed from this, yeah? Minus 1/6 z plus 2 to the 6th power plus 1 over 120 z plus 2 to 12th? I don't know, it doesn't really matter. I didn't really need to keep so much. All right, now, what do we have? Well, we have this function right here we can think of as the g of z in the theorem, right? It is analytic at -2, and g of -2 is equal to 1, which is not equal to 0. See, with a chalkboard, I could create more hideous sounds, even more. See, I actually don't mind the sound of fingernails on a chalkboard.
No.
I can just do it. It doesn't bother me.
No, it's the feeling.
Just thinking about it, like everything's.
I just wish I wish we had a chalkboard here so I could demonstrate for you how it doesn't bother me right now. So that is analytic. It's non-zero, and f of z is g of z over this, which means z not equal to -2 is a pole of what? Right, pole of order 2. Yay! All right. Next theorem. Theorem 9.29. We have let z naught be isolated singularity of f, period. Then z naught is pole of order n if and only if 1 over f is analytic at z naught and has, wait, what am I doing? At z naught and has z naught as a 0 of order n. All right. So can we prove this thing? I mean, I hope so. Oh, man. My own stupid feet. Let's see here. All right. So let's do this direction, right? Z naught's a pole of order n. So we can write f of z is equal to what? G of z over z minus z naught to the power n, right? Where g of z is analytic at z naught and g of z naught is not equal to 0, right? Thus, 1 over f of z is what? Well, z minus z naught to the n divided by g of z, right? Is 1 over an analytic function analytic? Because this has the form z minus z naught times 1 over g of z, right? Note, d dz of 1 over g of z is equal to minus 1 over g of z squared times dg dz, right? So is 1 over g of z complex differentiable? I mean, I think so. I do need to know that g of z naught is not equal to 0, right? So in short, yes, 1 over g of z is a analytic function at z naught. you'd be like, well, if it's analytic, what's its power series? Well, it's a pain to actually calculate, but the point is that this is analytic at z naught with, 1 over g of z naught equal to what? I don't know what it's equal to, but it's not equal to 0, right? And what did we learn last time? If you have an analytic function, right, and you can write a formula for it that's z minus z naught to the power. Oh, come on, guys, let me do that. If you had said something, I wouldn't have had to do that. So anyway, I'm saving that marker. So that proves that z naught is a 0 of order n, right? For 1 over f. Now we go the other way, right? If 1 over f is analytic at z naught, well, let me not even write it down. Let me just write down what that means. If 1 over f is analytic at z naught with a 0 of order n, that means that I can write 1 over f of z is equal to z minus z naught times some h of z, right? Where h of z is analytic at z naught, and you guys didn't correct me again. I give you a chance. Okay, it wasn't long a chance, but there we go, n. 0 of order n. So flip it. We get f of z is equal to what? 1 over h of z upstairs divided by z minus z naught to the power n. Yeah? But you can just think of the 1 over h of z as the g of z in the theorem, right? Is that analytic? Yes, it's analytic because the reciprocal of an analytic function which has a non-zero value is still analytic at the point. Which then proves that z naught is a 0. It's not a 0, but this proves z naught is a what? Pole of what? Order n. All right, great. Well then, if that's the case, let us look at an example. Let's see here. Example number 3. F of z 1 over, let's say, sine of z. Where does that have a pole? Where is that singular, guys? 0? That's a start. Pi? 2 pi?
Plus or minus.
If only there was some way to write this. 2 pi k is half right.
2
Pi k.
Pi k. Yeah, pi k is over. So this has singularities at, let's say, z sub k equal to pi k. All right? What kind of, what's the order of the pole? Let's see here. So 1 over f of z, right, is equal to what? Sine z. One, right? And notice that d dz of 1 over f of z is actually equal to what? Cosine z, right? So since sine of zk is sine of pi k, right? Which is 0. And cosine of zk is cosine pi k, which is what? Minus 1 to the k is all you want. Think about k equal to 0 is 1, right? K equals to 2 is 1, but close. So that's that. Of course, this is not equal to 0, right? So what's this? This shows sine z has 0 of order 1 at z equals to zk. In other words, sine z has a simple 0 at zk, right? And so by the theorem that we just looked at, this implies what? F of z equal to, goodness, cosecant z, more probably popularly understood as 1 over sine z, has simple pole at zk equal to pi k for any k in the integers. I calculated this a really different way in the notes. Interesting. Let's take a second to look at what I did in the notes. It's kind of funny. So what I did in the notes was I looked at 1 over f of z is equal to sine z. And what I did was I added and subtracted pi k. So I was like minus pi k plus pi k. Right? Adding 0. And then adding Engel's formula for sine gives me the sine of z plus minus pi k times the cosine pi k plus the cosine of z minus pi k times the sine of pi k. Of course, the second term I just wrote is needless because that's 0. And so what we have is minus 1 to the k times z minus pi k minus 1/3 z minus pi k cubed, and so forth and so on. That shows, right, that you can, I mean, one more step, I guess. This is z minus pi k times what? Times minus 1 to the k minus 1/3 times minus 1 to the k z minus pi k cubed, squared rather, plus dot 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 dot, right? So this right here is analytic at pi k and non-zero. Which shows again that pi k is a simple, what did I do? You guys are smiling. What did I do? I did something. What's up here? What's happening? Something's going on here. I can sense it. She did something. What did she do? She did something. I can tell it. Something's going on. It's like that scene in the chocolate, Charlie and the Chocolate Factory. Oh. Boy dresses in blue. All right. Anyway, there it is. I'm going to move on here before. I don't know what's going on here. Something's happening. You can't blame students that are not here. It's not allowed. All right. Let me go on here. So, let's see here. Next example in the notes is pretty easy. We'll look at that briefly here. What example I'm on? 4. So here we have f of z 1 over z cubed times z minus 2 minus 3i to the 6th power. So from that, I can pretty much immediately read off using the previous theorem 2 things. The one is that we have pole order 3 at z naught equals to 0, and I can also see directly from this that we've got a pole of order 6 at, let's say, z1 equal to 2 plus 3i. All right. To be clear, the reason I can do that is what's present in the formula besides the division by the pole term is non-zero at the pole and clearly analytic there. All right? Yeah?
Why is it clearly analytic?
Because like 1 over z cubed has no trouble at 2 plus 3i.
Okay.
On the flip side, 1 over z minus 2i minus 3i to the 6th power
Has trouble.
has no trouble at all at 0. So they respectively behave as the, oh man, did I erase the theorem? I erased the theorem. Oh well. Anyway. Let me move on here. Definition. If I can find it. Let's see here. It's one of my favorite complex analysis words. We say F is meromorphic on a domain D if F is analytic on D except possibly at isolated singularities each of which is a pole. All right. To be clear, a pole of finite order. Some people might say an essential singularity is like an infinite pole, but anyway. So this is meromorphic. I had this great class from a Russian named Takishan at Stony Brook. He was a vertex algebraist, vertex operator algebraist, and he used to talk about meromorphic functions, and the way he said it, it was just magical. This man also had the best pi of anybody I've ever seen. Like I tried to emulate it, but like it's just, I mean, my pi is sophomoric compared to his pi. It had like the hook down here and the other hook over here, and it was just perfect. It was, and like chalkboard too. Like, you just had to see it. It was, I remember it now, even now. He's a great professor. So some examples. Let's see here. F of z equal to, say, sine of z is meromorphic on C. But not C unioned with infinity, since what? Infinity is an essential singularity for sine. You guys remember that? if we look at the g of w, which is the sine of 1 over w, what do we get? Right? So if we form the corresponding reciprocal function for sine, that is got it. So the g of w, which is sine of 1 over w, has an essential singularity at 0, which by definition shows you that sine has an essential singularity of at infinity. Right. And the same story can be repeated for what else? Same song and dance for cosine z, cosh z, sinh z, e to the z, lots of things like this. Pretty much all of your functions which are entire on the complex plane, yet they almost all of them have infinitely many terms in their Taylor expansion, which when you look at what that means for the reciprocal expansion at 0, it's going to give you infinitely many reciprocal terms for the g of w, if you think through it, which means you have an essential singularity at infinity for all these. So you might start to wonder, is there anything meromorphic on the entire complex plane, right? So what if we had f of z equal to, say, p of z over q of z? Hey, forget that. Let's call it n for numerator over d for denominator. There we go. Where n of z and d of z are polynomials. So this would be an element of what I would probably call q. Oh, my bad, not q. This would be an element of c parentheses z. This is equal to rational functions. Over c. So a ratio of two polynomials, right? How can you rewrite that? Any rational function, we can rewrite in what form? We can rewrite it as f of z is equal to, let's say, like f naught of z plus r of z divided by d of z. I'm using r for remainder, right? So you do long division. Long division rewrites this as a polynomial plus a quote-unquote proper rational function, right? And here, the degree of r of z is strictly less than the degree of d of z. Yeah? So what can you guys tell me about this? Is this meromorphic on the complex plane? Forget about infinity for a second. How about just the complex plane? Is this meromorphic? First of all, where is it analytic? Let's talk through it. Where is it analytic? So this thing is wherever d of z is not equal to 0, right? Wherever d of z is not equal to 0, we can take the complex derivative of this. We know how. Yeah? So this only has singular points in the complex plane where? So it has, isolated singularities where the zeros of d of z. Those are the only places where you have a finite number of isolated singularities. Therefore, this is meromorphic on C. But is it meromorphic on the extended complex plane? What do you guys think? Well, think about this, right? If we go back here and we look at 1 over f of z, right? Oh man, I feel like, I don't think this is in my notes, but I think there's an extension to like this theorem to the case of infinity, you know? Like if this theorem extends to infinity, you know? If theorem 9.29 extends to infinity, what do you guys think? Does that theorem extend to infinity? I don't believe that's in my notes, but you know, it occurs to me right now it ought to be. I bet this is true. Let me at least say it in words. Let z naught be an isolated singularity of f, and let's think of that being at infinity. Then z naught is a pole of order n at infinity, if and only if 1 over f is analytic at infinity and has z naught as a 0 of order n. If that theorem's true, let's suppose it's true for a second. Maybe I'll make that a homework problem for you guys. Then we could simply look at 1 over f of z for this, right? Flip the script and give the same argument, right? You just flip it, long divide it, and well, I don't know if well, anyway, so like if I flip it, I just have what I've got, you know, d of z over n of z, which I can, if the degree, of course, if it's already proper, if it's already a proper rational function, right? If the degree of d, I can always do long division. Sometimes the polynomial piece is stupid, you know? So like, let's say this is h0 of z plus r0 of z divided by n of z, right? So you've got a polynomial piece and a so if the remainder is 0, then well, anyway, I should turn this into a homework for you guys. Let me stop thinking about it right now. I should turn this into a homework. I'll try to write up a homework on this. Yeah, it's not currently in the homework, but I should write this up. What? I shouldn't? Sure? Oh, okay, sure. What? All right, so the other way to argue is what? If we just go directly from the definition so the question I'm quibbling with at the moment is like, is f of z analytic at infinity? Or does it have a singularity? And if so, what's the order of the singularity, right? So if we look at g of w equals to f of 1 over w, what do we get? Using my expansion right here, we get f naught of 1 over w, right? Plus, you know, r of 1 over w divided by d of 1 over w. But the thing is, with this, notice that the degree of r is less than the degree of d. So, if you can imagine this, like the leading term in the so the leading term in the denominator has a larger order than the leading term in the numerator, which means that you're going to have like a 1 over w excess in the bottom. So if you sort through the details of this, this ends up being analytic at 0. So this is actually analytic at 0 if you sort through it. Again, because if you expand these as, power series, the degree of the denominator has a larger, the leading term in the denominator is larger than the leading term in the numerator. And as such, you have a larger power of 1 over w down here. So when you go through the simplification of the expression, you end up with overall a power of 1 over w positive in the denominator, which gives you a net power of w when you were to look at the Laurent expansion of this piece. But this, on the other hand, is singular, right? It's singular, and whatever the degree is of the polynomial, that's the order of the pole at infinity. All right? So let me just cut through the nonsense here and just tell you a specific example, what I'm claiming. So example 7, if we had something like f of z is equal to z cubed plus 2z plus 1 minus 1 over z to the 10th plus 1 over z minus I to the 13th power. All right, that's my rational function. That is a meromorphic function. This is meromorphic on the extended complex plane. I've forgotten my symbol for extended complex. I think it was C star. But anyway, why is that? Well, it has where are the singularities? Well, the singularities are at 0, at I, and at infinity, with orders, what? At 0, you have an order 10 singularity. At I had an order 13 singularity. And it turns out that when you look at this and study, well, you can even see this one, right? If I just plug 1 over w into that, I have a 1 over w cubed as my leading reciprocal power. So I get a 0, not a 0, but a pole of order 3 at infinity for this one. So yes, apparently every rational function is meromorphic on the extended complex plane. All right? Let me show you something. Oh, I think I misspoke about the Casarati-Weierstrass theorem last time, slightly, because the theorem I was quoting was Picard's theorem, and I didn't quite quote it right. Picard's theorem is a little bit more nuanced than what I said. It's not that you can approach any, well, anyway. Well, let's just look at the theorems. I'm not sure I said it quite right last time. Let's see here. Come on. Oh, yeah, let's not put email on the screen. All right. So this is where we started today. So this was the Casarati-Weierstrass theorem. Z naught's an essential isolated singularity. Then for every complex number W naught, there exists a sequence such that f of zn. Oh, okay. The limit is W naught as n goes to infinity. Okay, I think that's what I said. That's actually true. Fine. But Picard's theorem says something even a little bit more weird. And yeah, that's probably the same Picard as the Picard iteration we talked about in the other class. But it states for an essential singularity Z naught, for all W naught except possibly one value, there is a sequence Zn goes to Z naught for which f of Zn is equal to W naught for each n. So it's not just that it limits to W naught. You can find a sequence that as you get closer to the point, the central singularity, it's always attaining the value W naught at each point in the sequence. Ka-chunk, 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 ka-chunk. That is, it's just such wild behavior. So like, for example, e to the 1 over z, which has an essential singularity at 0, you can't set up a sequence which is 0 because the exponential never takes 0 as a value. But anyway. But according to the Kazareda-Weierstrass theorem, you can find a sequence of values whose limit is 0. So you can do that, which is what I was talking about last time. All right, let's go on. So there's the, we've already covered this stuff, right? So this is what I was just talking about. E to the z has an essential singularity at infinity, therefore it's not meromorphic on the extended complex plane. On the other hand, a rational function is meromorphic on the extended complex plane. Let's see here. Here's another example, which I'll skip over. So the interesting thing past my current example is that not only are rational functions meromorphic on this C star is C union infinity, okay? Not only are rational functions meromorphic functions, they're actually all of the meromorphic functions. If you have a meromorphic function on the extended complex plane, it is a rational function. So that's kind of neat. The only way that you can get, only poles, isolated singularities of finite order at both points finite and infinite is to have a rational function. And the proof is here, which I'll run through quickly. If you had the number of poles of f must be finite, otherwise they would accumulate to a give a singularity which was not isolated. So if f is analytic at infinity, we define p infinity of z to be f of infinity. Otherwise, f has a pole of order n, and p infinity of z is a polynomial of order n. In both cases, f of z minus p infinity of z is analytic at infinity, with f of z minus p of z going to 0 as z goes to infinity. So we're going to label the poles in the complex plane as z1 through zm, and we're going to let pkz be the principal part of f of z at each singularity. So at each each singularity zk, there exist constants alpha 1, alpha 2, alpha nk, such that the principal part can be written as a sum of these reciprocal powers, with the highest power being the order of the pole, which we're calling n sub k. And of course, you can easily see that this goes to 0 as z goes to infinity, right? If you've got a sum of reciprocal terms as z goes to infinity, this term goes to 0. Right? And that indicates that pk actually is, this is actually analytic at infinity, all right? Then we define g of z as the difference of f of z minus p infinity of z minus the sum of the principal parts, like this, all right? This g is analytic at each of the poles, including infinity, all right? Why is it analytic? Well, the reason this is analytic at each of the poles is you're subtracting off the part that misbehaves. So this gets rid of the part that misbehaves at infinity. This gets rid of the part that misbehaves at all of the finite poles. So the net result is a function which is analytic everywhere on the extended complex plane. And it's an entire function, and also g of z goes to 0 as z goes to infinity. Then by Liouville's theorem, g is bounded and therefore constant. It's 0 for all z and c, but g of z being identically 0 on the complex plane means that g of z is equal to, well, that means that f of z is equal to a sum of its value at infinity, which is either a polynomial or a constant, or 0, plus the sum of the principal parts. But this is exactly the partial fractions decomposition of a rational function. So the proof pretty much just rests on a clever, accounting of where the thing is singular paired with Liouville's theorem. But there it is. And this proves also that there is a partial fractions decomposition of a rational function. every rational function has a partial fractions decomposition. And you can look at that partial fractions decomposition as a sum of like a polynomial piece, right, plus parts which are singular. Right. Now, we weren't thinking of it like that when we did this stuff before, right? It was just an annoying algebra problem that I didn't really test on. Sorry about that. But we'll get back to it. We'll get back to it. Right. Okay, so now if you look here, I don't use any of the technology in Saf and Snyder. Right. If you look at these arguments, I'm just doing everything Calc 2 style. I'm just equating coefficients, plugging stuff in. There's nothing especially special about these calculations. Love them, leave them, whatever you like. All right. Oh, maybe this one's worth looking at. This one's worth looking at. How partial fractions helps us find the Laurent series. So in the last example, I showed that we can rewrite 1 plus z over z to the fourth minus 3z cubed plus 3z squared minus z as the sum of these proper rational functions. All right. If we want to find explicit Laurent series about z equals to 1, we simply need to expand the analytic function 1 over z as a power series. Now, what about these other three? Why don't I have to do anything to those if I'm looking for the Laurent series around z equals to 1? These are already expanded about 1, right? There's nothing to do. They're already part of a Laurent series at 1. But this is not like the others. This one does not belong. So to expand that about 1, I add and subtract 1, also known as adding 0. Geometric series that thing. There you go. That's what this expands to about 1. Of course, this piece is analytic, whereas this is the principal part of the singularity at 1 for this function. I can see that it's a 0 of order 3. It's a 0 of order 3. That's the top reciprocal power. And so lo and behold, here is the Laurent series for f of z at 1. Okay? What would the Laurent series for this function be about 0? That's more annoying for this expression. This piece is already done. If I'm expanding about 0, 1 over z is already part of a Laurent series. But these guys are not the right format yet. Yeah? So if I want to just calculate it directly, I can convert this to a Laurent series centered about 0 simply by finding the Maclaurin series for it. In fact, every one of these I can find the Maclaurin series because each one of these is holomorphic at 0. So I'm just finding the Maclaurin series for each of these, which really boils back down to calculus 2 tricks. Use the geometric series on this. This one, if we integrate, it gives us a reciprocal function, which can be geometric series, the reciprocal function. This one, if we integrate once, integrate twice, we get to a reciprocal function, which we can geometric series, and then differentiate back to get back. That's all I do down here. This is just straight Calc 2 that you guys have forgotten. But maybe you haven't. I don't know. I shouldn't be so. I mean, maybe you remember. I don't know. But this, if I integrate this, I get that. But I can geometric series that, like I was just saying. And as such, this is the, well, this was the geometric series. This is the series for the integral. But then to differentiate to get back, I get that, which gives me that. All right. And the other one, this one, I have to integrate not once but twice to get to the thing I can apply the geometric series result to. And then differentiate 2 times to get back to that is the Maclaurin expansion for that other term. And then once you've got all Maclaurin, all power series centered about 0, then you can add them together. And lo and behold, here is the Laurent series centered at 0 for this function. All right? All right. So now, do you actually need to find the full Laurent series for a function? Well, that brings us to chapter 10, the residue calculus. All right. And basically the answer given here is, no, we don't really care about the full Laurent series when we're interested in certain questions, right? So let's look at this. And